Hello everyone, welcome back. Now that we have seen the introduction of bifurcation in the part 1 video, let us get into this part 2 video where I will be introducing the saddle node and transcritical types of bifurcation. So what is this saddle node bifurcation? So these bifurcations, they are the basic types of local bifurcation. So saddle node is the very fundamental form of it. It is also called as tangential or fold bifurcation, where we will have the two fixed points which will collide and annihilate or destroy each other. Now that we have seen what a fixed point is, when can you call a fixed point to be stable, unstable? So the first type of bifurcation is the saddle node bifurcation, where the two fixed points will collide and annihilate each other. In discrete dynamical systems, it is also called as fold bifurcation, and this type of bifurcation is responsible for hysteresis and catastrophes. So to define a saddle node bifurcation, let us take the prototypical example, which is nothing but a ordinary differential equation of this normal form. dx by dt is equal to r plus x square. So how do we go with the mathematical analysis? We have to find the fixed points. We have learned what is a fixed point, right? So make f of x is equal to 0. So when dx by dt is equal to 0, r plus x square is equal to 0. So x square is equal to minus r. So x is equal to plus or minus root of minus r. So we get two fixed points here. But then think of the variation of control parameters. If r is greater than 0, root of minus r, so there will be no real solutions. So no fixed points exist in that case. If r is equal to 0, one fixed point, x star is equal to 0. If r is less than 0, root of minus r takes up the negative value. So minus into minus becomes positive. So two fixed points at x star is equal to plus or minus root of minus r for r less than 0. Now that we have got the fixed points, let us do the stability analysis. How do we do that? We get the derivative of f of x and substitute the fixed points into it and check for whether it is greater than or less than 0. So for the r less than 0, we got two fixed points. So let us substitute it into the derivative. F prime of x is equal to 2x. So for x star is equal to plus root of minus r, we end up with a 2 into plus root of minus r taking up the negative value, it will have a positive f prime of x. So it will be an unstable fixed point, often called as the saddle. Now for x star is equal to minus root of minus r, the derivative ends up with a negative value. We call it as a stable fixed point. Now at the critical point r is equal to 0, we will have a single fixed point. What about the r greater than 0? We will not have any fixed points, as inside the square root we will have a negative value resulting in the imaginary value. So we will not end up for any fixed points in the r greater than 0 case. This is beautifully depicted in the phase portrait. So we have got two fixed points for the case of r less than 0. One is a stable one denoted by a solid circle, and there is an unstable denoted by an open circle. Both of them collide. They merge together at r is equal to 0, the critical point, and then as we go for higher values r greater than 0, we will not have any fixed point. This is again shown here in the bifurcation diagram. So it is nothing but the x star varying with respect to the control parameter r. So for only the saddle node exists for r less than 0 case, and that is a stable one with a solid line for x star less than 0, and for x star greater than 0, it is an unstable fixed point. Now we can also see the reverse form of the prototypical form which we have seen in the last slide. So it was x dot is equal to r plus x square. Now we can check for x dot is equal to r minus x square. So as we do the analysis, we'll see that the entire behavior just flips up. So the mathematical analysis, we proceed in the same way. We end up with two fixed points. X star is equal to plus or minus root r. So here the fixed points exist only for r greater than 0 case, because square root of r we will have here. So for r less than 0, we'll end up with an imaginary value. So r greater than 0 only we will have two fixed points as plus root r minus root r. Now for r is equal to 0, only one fixed point. R less than 0, no real roots. Now let us check its stability. How do we do that? We take the derivative. So the derivative will be minus 2x. So as we substitute the x value root r for the minus 2x, we end up with a negative value in the x star is equal to plus root r. So that is a stable node. Whereas for x star is equal to minus root r, we will end up with a positive value resulting in the unstable fixed point. So this is beautifully depicted again in the phase portrait and in the bifurcation diagram. So for r less than 0, no fixed points. For r is equal to 0, we get just one fixed point. For r greater than 0, we end up with two fixed points. One is a stable one and another is a unstable one. Okay. So now the bifurcation diagram also clearly shows this behavior. For r greater than 0 case only, we will have the bifurcation, and it will be a stable one for positive values of the fixed points, and it will be an unstable one for negative values of the fixed points. So these two examples clearly say that there are going to be two fixed points, and these two fixed points, as we vary the control parameter, they are going to undergo a collision and they will get annihilated or destroyed of each other. So what is happening exactly here? There is a change in the number of fixed points. So there were two fixed points in the r less than 0 case, and for r greater than 0, there were no fixed points. And in this reverse form, it is just the ulta of it. So we get for r less than 0, we get no fixed points. They get created. Two fixed points are created as we go to r greater than 0 case. So this is saddle node bifurcation. So by this bifurcation indicates the presence of two fixed points and they get annihilated, or the vice versa phenomena. So as I searched through the internet for giving a real life example, I found this one, a very interesting one, and the source I have given here. It is a scientific article which shows that the shallow lake, its dynamics, it shows saddle node bifurcation. So what is saddle node bifurcation? There are two fixed points, and these two fixed points, they undergo a kind of collision and they disappear upon variation of a control parameter. So here too, in the shallow lake, there are two states. One is a clear water state with no addition of any impurities or any adulterants into it. Now as in nature, the ideal case can be a pure water state, but in nature what will happen? Some kind of addition of adulterants, some kind of addition of impurities will be there. So it will give rise to an intermediate state. So both these states could be called as the fixed points of the shallow lake. Suppose through the man-made intervention, some kind of nutrient loading is happening. So there is a kind of phosphorus, the nutrient gets loaded into this shallow lake. So what happens? These two states, the clear water state and the intermediate state, they collide and vanish into a sudden jumping to a turbid state where algae will get dominated. So the fixed points vanished. The clear state, intermediate state gone, and an algae dominated state emerged upon the variation of the control parameter. Here it is nothing but the nutrient addition. Beautiful, right? Now let us get into the second type of bifurcation called the transcritical bifurcation. So in the saddle node there were two fixed points, and then these two fixed points they merged, and then they too annihilated, destroyed each other. So there is a change in the fixed points, number of fixed points. Here in transcritical bifurcation, what happens is there is no change in the number of fixed points. Instead, two fixed points they collide and then they swap the stability. So the stable fixed point will become the unstable one, and the unstable fixed point becomes the stable one. So unlike other bifurcations where equilibrium points, the fixed points are created or destroyed, here they merely change the stability. So the best example for this transcritical bifurcation is this prototypical mathematical equation: dx by dt is equal to rx minus x square. So what do I do here? I'll do the mathematical analysis. So how am I going to get the fixed point? Rx minus x square is equal to 0. So x into, so if you take x outside, it is going to be x into r minus x. So we can have two fixed points. One is x star is equal to 0 and another one is x star is equal to r. So two fixed points. Now how do we determine its stability? Let us take the derivative. What is the derivative? R minus 2x. So substituting the first fixed point into the derivative, what do we end up? R minus 2 into 0. So it is merely R. So merely R case, if you vary the control parameter, what will happen? For R less than 0, we will have a stable fixed point. For R greater than 0, we will have an unstable fixed point. So for x, the second fixed point, R x2 star is equal to R. What happens? We substitute this R into the derivative, R minus 2 into R. So R minus 2R is again minus R. So checking the stability, if we substitute the control parameter R less than 0, minus of minus R becomes greater than 0. So it is an unstable fixed point. For R greater than 0, it will be minus R. So it will be a stable fixed point. So what we had as a stable fixed point, now it is unstable, and what we had as an unstable fixed point, it changes into stable fixed point. So this is what is given as the transcritical bifurcation. So the behavior is depicted here in the phase portrait and in the bifurcation diagram. So here what happened? In the R less than 0, we had a stable fixed point and an unstable fixed point, right? So R greater than 0, the stable fixed point, it became the unstable one, and the unstable fixed point became the stable fixed point. So this behavior could also be seen here. So we had a stable and unstable fixed points. So the stable becomes an unstable in the case of R greater than 0, and the unstable became the stable again in the case of R greater than 0. So this is the transcritical bifurcation. Now I also wanted to give an example for transcritical bifurcation, and I found this one. So this transcritical view of the matchstick. So this matchstick, if you take, it can be in two states. One is a unlit state and another is a glowing state, or which you say it is burning state of a matchstick. So we get two states. One is an unlit state and another is a lit state. So if you strike the match too softly below a particular threshold, below a particular threshold value of that rubbing force, which you call it as the control parameter, what will happen? The unlit state will be the stable one. Any simple tiny spark whichever is coming down will just quickly cool down, right? And the match will remain in the same unlit state. But what happens when you strike it hard enough? Then it will go beyond the threshold and the stability exchanges. Now it will glow. So, and what will happen? The unlit state becomes unstable, and even a single spark will trigger to a new stable burning state. So when that force given is less than 0, the unlit state was stable and the lit state was unstable. But when you give a faster strike, these states, they exchange their stability. The unlit state is now unstable and the glowing state is stable. So thus, this maths and physics, they find and they beautify the real life experiences, and this is the transcritical bifurcation. So that's it. So we have seen two types of bifurcation in this video. So happy learning again. So let us get into the part 3 for two other examples of local bifurcation, namely the pitchfork and harp bifurcation. Thank you. Stay tuned.